Narek,
Okay, we can hear you. Yes, yes.
Yes, we can hear you, Massimo. Now we can. You were muted. Now we can hear you.
okay. So I was mentioning the 4 items of science activity in 2024. The supernova studies, the connection gamma ray burst, and especially the study of interaction with the circumburst material. Basically, the circumburst material is related to the mass loss of the progenitor, and the mass loss of the progenitor, once we know the metallicity, is related to the mass of the progenitor. Then the study of nova rate in M87, where we have identified new evolutionary channel to explain the high nova rate. Basically, we show that the bond accretion is sufficient to trigger nova explosion on single white dwarf instead of binary, only in binary. Then we studied this new class of mysterious objects, intermediate luminosity transients. They are known also as nova or supernova imposters. And the idea is that they could be objects with a mass in which the progenitor have a mass between 8 and 10 solar masses. They are exactly in the transition interval of masses between the so-called low mass stars, less than 8, that will never explode at supernovae, and stars that will explode as a core collapse supernova. And finally, that is really a big issue. We are ready for commissioning our spectrograph SOX that will operate at NTT for the next 10 years, and through which we will going to observe a huge percentage of the most interesting transient object that will be discovered by LSST, the Vera Rubin telescope. Okay, recently we have started to work on this, let's say, enigmatic population of galaxies in the early universe that have been discovered by James Webb Space Telescope. And this galaxy, just to give you a short summary, are characterized by this red coloration. They are remarkable compact, and they start to be observed as at 12, so 0.4, 0.5 gigayears after the Big Bang.
They are observed up to
Z12.
Namely, this is a fact.
Yeah.
Up to Z equal 12, you understand? Therefore, now how the hell? Okay, the previous talk by Gregory spoke very significantly about Sagittarius A, which is here.
Yes,
There.
very close.
Okay.
Yeah.
We are speaking about an object at Z equal 12. You see that they start to
12. Let's see. Sorry, start from right side. 12, and then you go this way.
They go up to Z equal 12. How can any person who is not one of us in this room have the courage to try to relate an object Z equal 12 with an object in the galactic center? This is the question. I mean, how can anybody? Of course, there are people who are terrified that I use model rotating and so forth. But this is much more we're speaking about. And not trying to relate an object is equal to 12. We have been bold enough to propose this.
But Okay.
to an object inside our galaxy.
So,
Is there any, now the point that it will show us that strangely enough, if you take this object inside our galaxy, okay?
okay.
Which is, no, just wait a moment, 4 10 to the 6. Out of this object, if you look, okay, something interesting is coming out. Okay, these are the magnitude, okay, versus Z.
Exactly. All these data come from this Kochevsky et al. Paper that has been published in 2024. They provided a catalog of almost 400 objects. So I plotted the optical, in terms of the optical luminosity that is expressed in terms of absolute magnitude versus redshift.
Okay.
So,
Aspetti un momento.
okay.
Sì.
You said this, you have done that conversion to this
What?
observation.
They give the apparent magnitude, and so that's once I know the redshift is easy to go to.
From the redshift, from the parameter, you get the luminosity.
Yeah. Okay. So we can identify here two patterns. The first one is pretty trivial.
The
Two patterns, and the first one is trivial. You don't see objects fainter than minus 16. Okay, and minus 16 from minus 16 going above, they are fainter.
there,
Faint objects. You see? Look at the absolute magnitude.
yes.
There are no objects of with an absolute magnitude of minus 15, minus 14, minus 12, minus 11, minus 10. They are missing, okay? Just to give you an idea, minus 16 is more or less the absolute magnitude of the small Magellanic Cloud. And that is clearly, very likely, is due to an observational bias. Even James Webb cannot observe fainter object than that. Much more interesting is the second pattern, this one. You see, the bright objects, brighter than minus 20, they start to appear at the redshift between 8 and 9. And so there is an observational bias that from which we can expect to observe a faint object at larger distances than bright objects. And it is not an effect due to the density. You say maybe there are just a few ones, because the volume that we are sampling at Z10, 11, 12 is much larger than Z8. So that is a physical effect.
That they are not existing big object at the equal larger than 8. And this, I think I understood. And I can explain, we can explain. But it's very interesting, this.
Are you absolutely sure that the volume you are something relatively larger? It's not actually so sure, because there's so many interactions.
Yes.
The nonlinearity with the
is marginally between 8 and 12 is marginally larger than
yes.
there.
Yes.
Okay. Yes. But it's not. But it would be very I mean, okay.
We
But
have,
I can check better. I can give you the right number. I have it estimated. Yes.
Do that
Yes.
and respond to Gregory.
Yes. It is marginally larger. Then what? Then let's say we are producing another plot. There is a paper by Green and Toll 2024 where they are able to measure broadline component in this, just in a dozen, for a dozen of objects. And you see again a clear pattern. The small velocity that are associated, we believe, to the fainter objects. No, sì, è la stessa cosa, sorry, excuse me, let me finish. The small objects, the small full width of Massimo are associated to objects that are observed as Z12. And as soon as we decrease the redshift, this full width of maximum increase. Okay, so if we go back to the previous,
But let me say a few words, because maybe they did not understand what they were speaking about. Excuse me, can you go back a moment?
here,
Now, otherwise, I mean, it took us a longer time to understand. And you cannot just. I think the key point is that of this object, there are some in which they measure they measure a velocity of h.
yes,
Of h.
it's like in Cipher Galaxy, is in AGN, is that kind of measurement.
We are speaking about general relativity. Do you mind to explain a few words?
Yes.
Therefore, you are looking at some, first of all, they are not all the objects. There is a class of object, 10, special out of 300, otherwise you don't understand the difference between the two. There are 10 objects which are special out of the previous one. And these objects which are special, they can measure velocity moving around, okay, in orbit, at velocity of
Between 1,500, 2,000 up to 5,000.
5,000 kilometers per second. You understand? We notice around this object velocity. Well, it tells you, of course, if you look closer, but no, we are speaking about this object. And we have to understand simply what this tells us, that around this object there is something moving around this 10 between 1,000 and 5,000. Okay? Therefore, there is something interesting there, because the highest velocity are at z equal 4, the highest velocity. The lower velocity are at z equal 12.
Okay. And if you go,
You understand what this means a lot.
Okay, and now if
No, but I hope you got the difference between his presentation and this. And please, we have to teach him to speak, not only to a few people, okay, or majority. No, let's see what physicists can be interested. Physicists can be interested that there is a Keplerian motion around this object. But I don't want to explain. If you're not interested, I stop. But anyway, I have a duty to tell you. Therefore, if you look as a function of z, the highest velocity is equal 4. The one in the beginning has smaller velocity. Therefore, in a certain sense, this will tell that the mass of the object inside, the mass of the object inside, at z equal 12, is smaller than the one at z equal 4.
If you go back to the previous one, now, basically, if you put together the two plots, you can, you can associate the smaller rotational velocity to the faint objects and the larger rotation velocity to the more luminous and more massive stuff. That's the idea. Is that clear?
Out of those 12 objects you show in the second diagram.
These are 10.
Yes.
These 10. Okay, that's unfortunately I was not able to identify them.
That's
Okay.
how much they are
But,
biased with respect to this.
of course, but look at the fact that they have only data for 12 or for 10 objects is because to get the spectrum of that stuff, you need a lot of exposure time. So they cannot do that for 300 or 400 objects, impossible. But that's, okay, I will, I'm not sure that, I try to identify if I was possible to, because there are two different papers, you know, that's my mind. I will, of course, I will make an attempt for sure, but that's I'm quite pessimist about it. Okay. Then what happened? Okay. Yeah.
Quanti siamo? 1, 2, 1. Puoi dire alla cosa se può riservare per 6 o 7? Sì, grazie. Scusa. Scusa.
Okay.
Well, this is interesting. You said there 10, yes, but it's better than 0. And there is a trend.
Yes, I will try to make this his suggestion to identify this on the previous diagram, but
yes, we have done already. I 2 or 3 of them, I found them.
yes, but for another stuff. Okay, don't worry. Okay, let's go ahead other ways. Okay, now the point is try to identify. This maybe is something that you want to comment because it's your idea. Why we see the faint one a large redshift?
No, it's okay. Go on.
Is here to explain this trend. Here, the lack of bright object, very high redshift.
Io direi una cosa,
Sì.
perché dobbiamo ancora scrivere questo. Posso suggerire una cosa?
Dimmi.
Di far vedere soltanto quell'altra slides dove...
Quella della massa.
Della massa.
Okay, we have
Because
tried.
we want to convince you on one thing, that my guess that the center of the galaxy
As connected.
is related, just one. I don't want to annoy you with all the reason in my mind to do that. No, this is, it will be an offense. Let's look at one side.
Okay. Now, once
Forget about everything.
the next challenge, you try to estimate the mass of these red dots, having only the luminosity, optical luminosity.
Only luminous. Only luminous, not looking at that.
No, okay. And then, there are empirical relation between optical luminosity and bolometric luminosity, and between bolometric luminosity and Eddington luminosity, from which...
Now, let me tell you a few words. I disturb you sending a paper by Fermi, because I never found a paper more beautiful to explain Eddington luminosity than the paper by Fermi. It's monstrous. When I read, because these people were using Eddington luminosity, but this is the reason we have to finish the paper, the book. But I found a place where Fermi refused to go and look inside the star in Trento. And then he never looked inside the star, even for a neutron star or nothing. He never did anything on the ground of that lecture. He did not look inside the star. He said, because you cannot go and measure inside the star. And then he gave us an example. For example, Eddington realized that inside the star is so hot, that atoms will be ionized, and that it is okay. But at the end, in a star, you could have, this is Fermi, one or two electrons still around the nucleus. He said Eddington, with Eddington. This is the Eddington luminosity. I enjoy reading that again, and I send to you. Because once the last electron or two are left, finished. You have no possibility to throw anything out. I mean, is the fantastic interaction between this one or two electrons left interacting with the large G of the ionized nucleus. Please, it's your work on this. To show that it's sufficient to bring the nucleus out. It's only Fermi who could do this. You see the beauty or not? It's only this one or two electrons which are left on the nucleus. Therefore, the nucleus acts on the electron with all its charge. But this electron is the only one which can feel the pressure of the radiation and bring the nucleus out. This is the paper by Fermi. Now, these people are using the luminosity of Eddington for this object. Eddington luminosity. Therefore, he will tell you, I think we have to go to lunch. If you have the Eddington luminosity,
I'm using the Eddington luminosity. I compute the Eddington luminosity from the optical, bolometric, true empirical.
Allora, you take the optical luminosity.
Yes, from the first block.
You go to the editor luminosity. Okay, let's stop here.
No,
and you compute the mass.
Yes, but I want to tell them something important, that I want to check out how good was my approximation to use the editor luminosity
Okay,
to
that
compute
is
the
the
mass.
case, but let's go to the
And
result.
I was,
No, it's not that you use editor luminosity.
what?
I mean, you assume that the luminosity is a fraction of the editor luminosity.
Of course, yes. And that, no, I take the optical luminosity, I transform that in bolometric, and from bolometric to
You assume that it's a
editor.
fraction of the editor.
Yes, and I want to check this approximation that I did, this series of passage. True, fortunately, I have this paper by Green, table 3. They use the full width of Massimo, the velocity that we were commenting before, to determine the mass of the object. Ma no, è importante questo, se
Fermiamoci un
no.
momento.